This video, we're going to go through section 5.6, which is the multiplication rule for independent events. So in the previous section, we talked about the general multiplication rule, which is listed here, where the probability of A and B is equal to the probability of A times the probability of B given A has already occurred. So it includes a conditional probability, because if events are dependent, then A happening has an influence on B happening. If events are independent, A and B are separate, and so it doesn't have that conditional probability for B. So the probability of A and B occurring, if I know A and B are independent, is just the probability of A occurring no matter what, times the probability of B occurring. Again, because there's no overlap in the events, because they're independent. So in this first example, a student has heard that spinning pennies on a table rather than flipping them in the air results in tails side up 65% of the time. Okay, so they're saying that the probability of spinning and it landing on tails is 0.65. If this is true, what is the probability a student who spins 4 pennies will have them all land tail side up? So that means they want us to find the probability that 4 pennies are spun and all 4 of them land tail side up. So we're finding this compound probability of a bunch of ands for the tails. So since I'm spinning the penny 4 times, I'm going to take the probability of landing on tails and raise that to the 4th power. So if I do 0.65 raised to the 4th power, that gives me about 0.1785. So it's about an 18% chance that they will land on tails every time. The next one is more complicated. It's an at least probability. And so at least probabilities mean that I'm going to have to add a bunch of and probabilities together. So if at least one lands tail side up, thinking about it that way, that would mean that maybe the first one's tails and the rest were heads. Or the first one's heads, the second one's tails, and the rest land heads. Or heads, heads, tails, heads, or heads, 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 tails. So that's all the possibilities for one landing tail side up. This says at least. So that means that I could also have 2 land tail side up, all the way to all of them landing tail side up. So this is a really big sample space in terms of what qualifies as this event. What's actually easier is thinking about the complement of this event, which is that none of them land tail side up. So if all of them land head side up, that's only one situation as opposed to an uncountable number at this point for landing tail side up, but at least one landing tail side up. So when you say the word at least, sometimes it's easier to use the complement. In this case, the complement would be the probability of the penny landing on heads 4 times. So the complement is the probability of it landing on heads 4 times. Remember that probability, to denote that it's the complement, is 1 minus the probability of it landing on heads 4 times. So what we need to know then is, what is the probability of this penny landing on heads? So if the probability of tails was 0.65, in general, the probability of landing heads would be 1 minus the probability of it landing on tails, because they're complements. So that would be 1 minus the 0.65. which means it's 0.35. So I'm going to do 1 minus 0.35 raised to the 4th power, because that would be landing on heads 4 times. So that's 1 minus 0.0150. So that means that it's about 1.5% chance that it would land on heads 4 times in a row using the probabilities given in the problem, which means that we have a 0.985, so 98.5% chance that it will land on at least one tail side up. Okay, so again, when you see the word at least, it helps to use a complement. So that the sample space is usually smaller for that event not happening than it is for that event happening. And so you find the probability of that event not happening and then subtract that probability from 1. The next one's a little bit different, but we're still using the multiplication rule for independent events. So we have a computer whose random number generator produces random integers from 1 to 50. They want us to find the probability that among the first 9 random integers generated, all of them fall in the range of 1 to 35. So we want the probability that we get 9 numbers and they're all 1 to 35 in that range. So what we want to think about is, what is the probability that we just get one number between 1 and 35? So we've got 35 numbers from 1 to 35 divided by 50 numbers in our sample space. So 35 divided by 50 is going to give us 0.7. So it's a 70% chance that I will pick one number between 1 and 35. Because I want 9 of them, I need to raise that value to the 9th power. Okay, so I'm going to take my 0.7 and raise that to the 9th power. If I evaluate that, that's approximately 4% or 0.04. The last piece went over mutually exclusive versus independent, because there's sometimes when students get those words confused. So remember, mutually exclusive events are disjoint events. What that means is that they don't have this overlap that non-mutually exclusive events have. So that means that the addition rule for mutually exclusive is missing that minus the probability of A and B occurring at the same time, because that value is 0 since they're disjoint. So know that if something is mutually exclusive, it is not independent, and vice versa. So those two things are mutually exclusive from one another as well. So if they are not mutually exclusive, they could be independent or they might be dependent. So there isn't a hard, fast rule in terms of that. But we do know that if something is mutually exclusive, it's not independent. And if something is independent, it is not mutually exclusive. And so there is a way to test whether something is mutually exclusive. And that's by taking the probability of A or B and checking to see if that is equal to the probability of A plus the probability of B. Similarly, to tell if something is independent, we would check the probability of A and B and see if that is equal to the probability of A times the probability of B. So let's look at an example asking us to determine if something's independent. Suppose among the 6,000 students at a high school, 1,500 are taking honors courses. I'm going to call that event A. And 1,800 prefer watching basketball to watching football. I'm going to call that event B. If 450 students are both A and taking honors courses and prefer basketball to football, are the events taking honors courses and preferring basketball independent? So we want to take the probability of A and B, that both probability, which is 450 students out of our sample space, our population of 6,000 students, and see if that value is equal to the product of the probability of just taking honors courses times the probability of just preferring basketball to football. So the probability of A and B both occurring using the 450 students is 0.075, so about 7.5%. Now what we want to do is find the probability of just A occurring. So we still are looking at the whole school, or among that 6,000 at the school, when we're finding these two probabilities. So we want to find the probability of A occurring and the probability of B occurring on their own. Okay, so 1,500 students. Let's do B first, since I can't change my pen. 1,800 students prefer watching basketball to football, so that is 30%, or 0.3. Then 1,500 are taking honors courses, so that means that the probability of A occurring is 0.25. So what we want to check is, does the probability of A times the probability of B give us the same result that we got from A and B? So if I multiply 0.25 times 0.3, do I get 0.075? And I do. So what this means is that these events are independent. And they're independent because the probability of A and B is equal to the probability of A times the probability of B. Okay, so if I got anything different, that would make them dependent, right? So if these two numbers didn't match, they would not be independent. They would be dependent. What I do know is that these then cannot be mutually exclusive events. Okay, so once I know they're independent, I also know that they are not mutually exclusive in that case.